All right, now we're looking at 4.5, solving polynomial equations. So we have solved equations for a long time, right? Whenever you think about math, you probably think about solving things, right? If you had something like, I don't know, 2x plus 4 equals 0, and you solve that, you have something like 2x is negative 4, and x is negative 2. Right, so that was solving a polynomial equation. That was a simple one. That was just a linear equation. Down here on number 30, we have a cubic equation that we're going to solve. So, starting off, we try to factor it like what we did in the previous lesson. I see that everything has a 4 in it, and everything has an x in it. So I'm going to factor out 4x. And then I still tack on this equals 0, and that's the new part for today. We're having that equals 0. From the 4x cubed, we'll have an x squared left over. From the 32x squared, we'll have an 8x. And then from the 64x, we'll have a 16. We can check ourselves here by distributing back in that 4x to all three of those, and we would get what we started off with. Now, so we have the 4x hanging out front. Now we want to try to factor the trinomial that's in the parentheses there. So I look for two numbers that multiply to be 16 there. That would add up to be 8. And that's going to be 4 and 4. So I can factor this to be 4x and then x plus 4 equals 0. Now I'm going to use the zero product property, and that we've used that before. Whenever we used it before, we normally only had two sets of parentheses here. But now we have two sets of parentheses and the 4x. So we really have, let me see if I can erase, we have the 4x, then we have the x plus 4, and then we also have the other x plus 4. So we're going to write those separately here. We have 4x equals 0, the x plus 4 equals 0, and then the second x plus 4 equals 0. Now we solve these three equations separately. We get x equals 0, x equals negative 4, and another x equals negative 4. And these are our answers. And previously, we would have just listed out x equals 0 and x equals negative 4. And those would be our answers. And those are our only answers. But the negative 4 happened twice, right? We had a negative 4 show up from this one and from this one. It showed up from the blue highlight right here, and then it showed up from the pink highlight, right? So it has a repeated solution, right? And right here I say that it has a repeated solution. So we're going to somehow state that. We're going to say x equals negative 4 with a multiplicity of 2. And this mult means a multiplicity. And let's see if I can spell that right. Mult. I'm thinking that's how you spell multiplicity, but I might be wrong. We will normally just abbreviate it to be mult. Okay? So from now on, we always want to be stating a multiplicity if there is. This x equals 0, I don't need to say multiplicity 1. It only happens once. You're only going to be doing that if it occurs more than one time. And what we'll see, and we're going to have that hopefully down farther, is that if you add these up, so we have the 0 occurring once, and then the negative 4 occurring twice. If you add those up, you get 3. And that is the degree over here of our equation. We had a degree 3 equation, right, because that's an x cubed, and we had 3 answers at the end. If it was a degree 4, we would have 4 answers, right? We might have multiplicity to get to the 4, or to get to the 3 here, but it would be different answers, right, multiplicity answers. All right, so that is solving. That's the simple solving. You just factor it and then use the zero product property. Next up, we have the rational roots theorem. And this is one of those that's sometimes kind of difficult to remember, sometimes difficult to apply, but we'll do our best here. If f of x equals blah, and that's the standard polynomial equation there, if he has integer coefficients, then every rational solution of f of x equals 0 has the following form. And to be rational means that it could be a fraction. So right here they have p over q. So that's like a general fraction there. The fraction with a numerator of p, denominator of q. They're saying the numerator has to be a factor of the constant term a sub 0. So that's going to be this a naught is the end And then the denominator will have to be a factor of a sub n, which is the very beginning coefficient. What this can be useful for is if you're really just hitting a brick wall and you don't really know what to do in a problem. Well, then you'd probably try to invoke the rational roots theorem and list out a bunch of different roots, and then check a bunch of different roots and see if they work out. Let's see how we can apply this to number 31. We're going to need to list out P over Q. Right? So that's going to be factors of negative 28 over factors of 1, because there's a 1 hanging out front in front of the x cubed piece. So looking back up what we had the negative 28 there. There's our negative 28. And then we have the 1, right? And it was like an understood 1. So let's list out all the factors of negative 28. So starting off, we're going to have positive or negative 1. Then we'll have positive or negative 2. Positive or negative 3 doesn't work. 4 works. You could divide 28 by 4. You could divide it by 7. You could divide it by 14. Divide by 28. I believe that's all the factors of negative 28. And then we have factors of 1, and this one's much more simple. We just have plus or minus 1. So now we need to list these all numbers out, and it's really convenient just because we have the denominator of plus or minus 1. Makes it much more simple. If that was a 2, then we'd have to list out a lot more. We're just going to have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 7, plus or minus 14, and plus or minus 28. These are the possible rational roots. So we're going to try to find 3 of these numbers here, right? So there's all these possible roots. We should have 3 answers because this is degree 3 polynomial, right? X cubed. So there should be 3 answers at the end. So we're going to take these numbers and we're just going to plug them in and see if they work. So I take an XYT chart and I'll have positive 1, negative 1, positive 2, negative 2. Next up we'd have positive 4, negative 4, positive 7, negative 7, positive 14, negative 14, positive 28, negative 28. And you could just plug all of those numbers in. Now I plug them in just so we can move quickly. And whenever I plug them in, I got a 0 for the negative 1, a 0 on the negative 4, and then a 0 on the positive 7. All of the other numbers were not 0. Okay, so you would plug these in and you would get something that was not 0. Now there's a way to quickly plug all of these in really quickly with the graphing calculator, and I'll show you how to do that in class. But if you're working on a normal calculator, not a grapher, you'll just have to plug these in a bunch of times. So what this means are that our roots, because we got the 3 zeros there, our answers are x equals negative 1, negative 4, and positive 7. And that's going to be our answer. Number 32. Again, we're going to try to not solve it. We're not going to solve it outright, at least. So I'm going to use the rational roots theorem again. We know that there should be 3 solutions. So I need to write out my P. Was it P on top and then Q on bottom? Yeah, P on top, Q on bottom. We're going to have factors of 3, or plus or minus 3. Oh, wait, no, we just write 3 there. And then next up we have the plus or minuses. And then factors of 2. Well, the factors of 3 are just plus or minus 1 or plus or minus 3. Factors of 2 are plus or minus 1 or plus or minus 2. So now what we need to do is we need to write out all of the different combinations of numerators with the denominators. So I'm going to use the denominator of 1 first, and I'm going to write out all the different numerators that would work with that. So I'll have plus or minus 1 over 1, and then plus or minus 3 over 1. So those use the 1 as the denominator. And you could put the plus or minus in the denominator as well, but having a plus or minus in top and bottom, it doesn't really matter. So I just normally write it in one time. Now for my other piece, I'm going to use the 2 as the denominator. So I will have plus or minus 1 over 2, and then plus or minus 3 over 2. Now, just like in the last problem, we have to plug in all, how many this would be? There would be 8 total different ones here. We need to plug all those in. So again, you can think about this as doing like a big t-chart, right? A big XY t-chart where you've got all these different x values that you're just testing out to see if they work out. I've already plugged all these in, and I got that whenever I made my like fancy t-chart, I had -1, 3, and 1/2. Those 3 numbers gave me 0. And while you're testing these out, you get to stop when you get to 3 zeros. Right? We know that up here we have a exponent of 3, meaning there are going to be 3 numbers that give you 0. Once I got to 1/2, I stopped plugging in, right? I didn't have to plug in the plus or minus 3/2 because I already found all of my roots by using the plus or minus 1, plus or minus 3, plus or minus 1/2. So I didn't even have to do this last one there because I knew there would only be 3 zeros. So my answer is x equals -1, +3, and then +1/2. Alrighty, there's 32. Let us move on to 33. All right, looking at 33 here. Now, one of the big differences between 32 and 33 is that this isn't equal to 0, right? In the previous two, in 31 and 32, we had it equal to 0 there, right? There's equals 0, equals 0. But in 33, we don't have that. So first off, we have to get him equal to 0. So I'm going to add the 3y squared to the left side. And then I'm going to have 3y to the 4th minus 6y cubed plus 3y squared equals 0. Now I want to pause and I want to think about how many unique answers should I have? How many different answers should I have? Well, we have a degree 4, so there should be 4 solutions. There might be a repetition in the solutions, but there should be 4 of them. We need to be able to account for all 4 before we're done. I'm going to try to factor this one because it's already just kind of looking like it's going to factor. We got a 3, a 6, and a 3. Those are probably going to factor. And then we got a y, and a y in all 3 of them. I'm going to pull out a 3y squared. Left over is going to be a y squared minus 2y plus 1 equals 0. And again, while I was writing that, I was kind of testing it out in my head. I was redistributing back in, making sure that it would work out correctly. Now I can actually look at here, and I have the left side with the 3y squared, and then I have the right side with the y squared minus 2y plus 1. Separately, I know that from this yellow chunk on the left, I'm going to get 2 roots from it, or 2 solutions. And on the right side, in the blue chunk, I'm going to get 2 solutions as well, right? And that's adding up to my 4 that I should get overall. So I'm going to get 2 from the yellow and 2 from the blue whenever we're all done. As I continue on, I'm going to have 3y squared, and this middle guy is going to factor. -1 times -1 gives me the -2. So I'm going to have y minus 1 equals 0. Now that it's completely factored, I can use the 0 product property. 3y squared equals 0, y minus 1 equals 0, and y minus 1 equals 0. From the left, the 3y squared gives me y equals 0. Then we get y equals 1 and y equals 1. Now written here, we have 3 solutions listed, right? We have the y equals 1. So we get a y equals 1 with a multiplicity of 2. And then we also have the y equals 0. But we're supposed to have 4 of them total. And what ends up being here is that the y squared there tells me that there's actually y equals zeros, right? You could think about this as 3y equals 0. And then you'd have y equals 0 from the first y, that would be like this one, and then y equals 0 from the second one. So we have a y equals 0 with a multiplicity of 2 as well. Together, these give me 4 solutions. So again, the process of doing these, the process of solving is you first get them equal to 0, and that's pretty standard for what we've been doing. Then you want to factor if you can. And then if you can't factor, we know that we can use the rational roots theorem to get us some potential answers. And then we check our potential answers. In 33, we were able to just factor everything, and it worked out very nicely in that way. Let's look at 34, and so we're going to get them equal to 0, like we did in the last one, and then we're going to see if we can factor. So I'm going to subtract everything to the left. That'll give me 8u to the 6th minus 16u to the 4th equals 0. Now, both of them have an 8. I could pull an 8 out of both, an 8, and I could pull out a u to the 4th. And then I'm going to have, what, u squared minus 4, and that's equal to 0. Now, I didn't write it in the beginning, but this is a degree 6 equation, so there should be 6 solutions. And then I'm looking at my break apart here. I've got 8u to the 4th. This is going to give me 8u to the 4th equals 0, and u equals 0. And that's going to have a multiplicity of 4. So I'm going to go ahead and write this. U equals 0 with a multiplicity of 4. And then this other piece, the u squared minus 4, we could go ahead and say u squared minus 4 equals 0, u squared equals 2, u squared equals 4, and then u equals plus or minus the square root of 4, which is plus or minus 2. So we have u equals 0, and then u equals plus or minus 2. And if you add those up, we have 4, 5, 6. So we needed 6 answers, and we've got our 6 answers. Now, right here, some of you might have noticed that that is a difference of 2 squares. We could have written this, we could have factored it more and said 8u to the 4th, and then u plus 2, u minus 2 equals 0. And that would be a good way to factor it. I'm just trying to show you a different way. You can break it apart into 2 more simple problems before factoring it completely if you want to. All right, let's look at 35. So we want to try to factor it, and if we can't factor it, then we try to do the zero products property. But we really don't want to do the zero products property unless we have, not zero products property, the rational roots theorem. There we go. We don't want to use the rational roots theorem unless we have to. I hope that we all agree. Let me see if I can get back to this page. That writing everything out for 31 and 32, that takes a while to write everything out. And it takes a while to plug everything in as well. So this is kind of like a last resort. If you can just plain old factor, you want to. In 35, all right, looking at problem number 35 here. We're supposed to solve again. This one has 4 terms, and the last one only had 2. The one above it had, well, it's not going to show me, 3. And number 32 and 31, they had 4 terms, and we had to do the long form using the rational roots theorem. On this one here, I want to try to not use the rational roots theorem because it takes a while. I'm going to look at the first 2 and the last 2, and I'm going to try to factor by grouping. And don't write this down because it's not going to work out, but I want to show you what I'm going to try to do. From the first 2, I'm going to pull out an n squared, and then I'd be left with an n plus 12. And then I want to try to look, how could I make the second piece, this guy, look like something with an n plus 12? And I'm just not seeing how we could make that work out. I'm just not seeing it. So this one would be unfactorable, or at least I can't see how to factor it. So we're going to need to invoke, or we're going to need to use the rational roots theorem. So I'm going to look for factors of p over factors of q. That's going to be factors of the 64, which is going to be plus or minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16, plus or minus 32, plus or minus 64. There's quite a few there. And then the other one is a little bit nicer because it's just plus or minus 1. So let's list out all of these. Actually, we kind of have them listed out here in the numerator. These numbers here, we're going to start trying to plug in. So I start off, and I'm actually I got my calculator here, and I type this equation actually into the grapher, and I've opened the table, and I'll show you how to do that in person sometime. And whenever I look at my table, I see that -4, right? If I made a t-chart with -4, it gives me a 0. So we know that one of my answers are going to be -4. But we should have 3 answers, right? There's an n cubed, so we should have 3 total answers. And if you look through all of the other answers, it's not going to work out. You're not going to get another 0. So it's not just -4. We're going to have to figure out where are the other 2 solutions, right? Because that n cubed means that there has to be 3 of them here, right? This is a cubic, so it has to have 3. So what we're going to do here is we're going to say that because this was an x equals -4, or x equals -4 there, we know that if we could factor it, the step before it would be that x plus 4 equals 0. Right? We'd have that factored over, and then we'd have an x plus 4, and we'd have something else equals 0. Right? We're kind of thinking backwards, as if we were actually able to solve the problem. So what I'm going to try to do is I'm going to divide this equation up there, that expression, by x plus 4. And I'm going to use long division for that. Well, I guess it's not x plus 4. It would be n, wouldn't it? This would be an n. That'd be an n. That'd be an n. That'd be an n. So I'm going to divide by n plus 4. Underneath it, we're going to have n cubed plus 12n squared plus 48n plus 64. Right, and again, what I'm trying to do here is I'm searching for my other 2 roots. We know that there have to be 3 roots total, and we have found one of them. It might be that that one has a multiplicity, but we don't know that for sure. We don't have a good way to check that yet. So I'm dividing it out to see what would happen if I was able to factor it. So we're kind of like forcing factoring to happen here. So I want to look, how could I make the n be an n cubed? Well, I'd need an n squared, so I'm going to take 1n squared, and then I'm going to multiply that and get an n cubed plus 4n squared, and then we're going to subtract this. That'll give me 0 plus 8n squared, and then I drop down the 48n. Next up, I'll have a plus 8n, because whenever I distribute out to this, it'll give me 8n squared, and then 8 times 4, I think I know that, but I'm going to type it in just to make sure. 32 plus 32n. Now I subtract this again. I get a 0, and then I'm going to have 48 minus 32, and that gives me 16n, and then I drop down the 64. Now lastly, I need to think again about what would I put here such that whenever I multiplied it, my n would be a 16n. Well, I'm going to need a 16 here. Then I distribute and I get 16n, and then 16 times 4 gives me 64. I subtract these and I get 0 and 0. So it all factors nicely, or it all divided nicely. All right, so what did we say here? We divided by the n plus 4, and we got n squared plus 8n plus, I didn't put the plus there, but there's a plus 16. What we are showing is we kind of forced it to factor. We are saying that n plus 4 times n squared plus 8n plus 16, this is equal to our original equation. Remember, in the very beginning, I tried to factor by grouping, but I couldn't do it. I couldn't figure out how to do it. So we found that 4 is a root, or negative 4 is a root, is a solution. So we knew that n plus 4 has to be a factor of it. So we divided by it, and we got an integer, or we got not an integer, but we got a non-remainder, right? And to get a non-remainder means that it actually divides out evenly. And if you take this and you multiply all this out, you'll end up getting what we had in the very beginning. So we forced it to factor just now. There's our equals 0. This right here, this is our n equals negative 4 that we had earlier. And this right side, because it's just a trinomial now, I'm going to see if I can factor it. I'm going to look for two numbers that multiply to be 16, add up to be 8. It's going to be 4 and 4. 4 plus 4 gives me 8. So now I'll have n plus 4, that's this guy, and then my other two, n plus 4. That's that one, that's that one. We have 3 n plus 4s. So if I look at all three of those, I'm going to have n plus 4 equals 0 and n equals negative 4, but that occurs 3 times, so it has a multiplicity of 3. And there we go. That's a very long problem. But there we finally have it. All of the problem, we're kind of chasing those 3 solutions, right? In the very beginning, let me go back to this, n cubed, right here on the upper left corner here, n cubed means there has to be 3 solutions. And we can't just, whenever we got to saying that n equals negative 4 using the rational roots theorem, we couldn't just say, oh, well, now we're done. The answer is negative 4. We can't do that. We have to actually check that negative 4 is the only answer, because we know that we have 3 answers, so it's either going to be a multiplicity or you have more than one answer. And there could be some wonky square root answers, and that's, I think, what we're going to look at next. Let me see. Oh, irrational conjugates. Let's read what we have here. Let f be a polynomial function with rational coefficients, right? That means with fractional coefficients. Let a and b be rational numbers such that root b is irrational. So that'd be like b equals, I don't know, 2, right? Square root of 2 is irrational, meaning it's a non-terminating decimal. If a plus root b is a 0 of f, then a minus root b is also a 0 of f. That's a neat idea there. And that comes back, the way that I understand that best is that you think about in the quadratic formula is a plus or minus the square root. Hopefully we all remember that. This b is kind of underneath the square root, and the a is hanging out front. So it's a equals plus or minus the square root. And let me also just say that this a and this b, they are not the same a and the same b as whenever we have ax squared plus bx plus c. They are different a's and b's. Maybe they should have been a different letter, but they're the same. Let's look at 35.2. Write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and zeros 3 and 2 plus root 5. So what happened is somebody solved the problem, right? They solved the problem like what we did in the last one here, number 35, and they got the answers of 3 and 2 plus root 5. And we're supposed to write the equation. So first off, we have to look at the 2 plus root 5 and say, well, there's also going to be a 2 minus root 5. Right? If there's a positive one, there has to be a negative one, and that comes back up to here with thinking about the quadratic formula and the plus or minus there. So we now have 3 unique roots. We have 3, 2 plus root 5, and 2 minus root 5. We have 3 different solutions. Now, thinking back to what I did in the last problem, where I had the, I'm looking in this region right here. We got the n equals negative 4, and then I kind of put it back into what if it was in the equation. That's what we're going to be doing here. We know that this 3, there had to be a x minus 3 somewhere, because then he would be equal to 0 and you solve. So the next one's going to be x minus 2 plus root 5. You see how I put the parentheses in there, right? I didn't have to put the parentheses in there for the 3 because it was all alone. Next up we'd have x minus parenthesis 2 minus root 5. The rest of the problem is just prettying this up. We want to write him in standard form. So I'm going to distribute the negatives. Then I'm going to have x minus 3, x minus 2 minus root 5, and x minus 2 plus root 5. Now, in these problems, what I would suggest you do is you leave the beginning all alone, or whatever the plain piece is, the piece without a radical. I would leave him alone. So in this next step, I'm just going to have the x minus 3. But then multiply out the radicals first, because radicals should go away in a polynomial of this situation. So I distribute, and I'm going to have x squared minus 2x plus, I'm going to say x root 5. And I'm going to stop drawing the swoops because they're taking up too much space. Distributing the negative 2 out, the negative 2 right here, I'm going to have negative x plus 2x minus 2 root 5. And then distributing the negative root 5, excuse me, we'll have negative x root 5, positive 2 root 5. And then lastly, I have negative root 5 and positive root 5 gives me a negative plain old 5. Now we look for canceling roots, and they should cancel. Negative 2 root 5, positive 2 root 5, those cancels. Positive x root 5, negative x root 5, those cancel. So in our next step, I'm going to combine like terms, and I get x minus 3, and then I'll have x squared. That's that first term. Then we have negative 2, 3, positive 2, so we're at negative 1 now. So negative x, and then on the end, I have a negative 5. We're almost done. I'm going to bring it over here, and I'll have x minus 3, x squared minus x minus 5. Now I need to distribute again. So we're going to have x cubed minus x squared minus 5x minus 3x squared plus 3x plus 15. And whenever I add that up, I get x cubed minus 4x, x squared, excuse me, minus 2x and then plus 15. So that's going to be my answer. Now we need to make sure that we wrote it in a nice way. They said they wanted it to be a function. So I'm going to say that this guy is equal to f of x, where f is a function there. Right, so again, what we did in this problem, it was a long problem again, is we were given the answers here, right, the solutions, and we wrote a function who has the x-intercepts, or the solutions, or the roots, whatever term we want to use, of 3, 2 plus root 5, and 2 minus root 5. All right, example 35.5, we're supposed to discuss multiplicity and tangent and how they relate to the x-intercepts here. So I'm going to take my graphing calculator and just draw a rough little sketch here for us. We have x to the 4th plus x cubed. If you have a graphing calculator handy, that would be a good idea to type this in here. 1, 2, 3. It looks like we have an x-intercept at negative 3, at 0, and then at 2. And it looks like it does something roughly like this. All right, that's not a perfect graph, but it's a good enough graph. This guy here, he's a quartic, right? He's degree 4. So there has to be 4 solutions, 4 times that this guy is equal to 0. But on the graph, there's only 1, 2, 3 times. And it's not that I didn't zoom out far enough. It's not that. It's that there is the 4th one hidden here. I want us all to look at the middle one, the x equals 0. That one just barely touches the x-axis. That means that there's going to be a repeated root there. We don't know how many times it repeats, but it has to repeat an even number of times. So what we have here, roughly, a general rule is if it crosses the x-axis, it occurs 1, 2, 3, 5 odd numbers. There's a of 1, 3, 5, something like that. It repeats an odd number of times. So either it only happens once, or it happens 3 times, 5 times, 7 times, so on. If it just is tangent to the x-axis, it has a multiplicity of 2, 4, 6, or so on. It has to occur an even number of times. So right here at 0, we know that that has an even multiplicity, whereas the other two has to have an odd multiplicity. So our actual answers are going to be x equals negative, is it negative 3, equals negative 3, and then it's going to be 0 mult, M-U-L-T, 2, and then also at 2. And that ends up adding up to be our 4 different roots. So on all of these problems, whenever you're doing it by hand, they are long problems to do. If you have a grapher handy, I would graph them and have the grapher help guide your decisions or help guide your process. It's not that the grapher makes it easier necessarily, but it just means it such that you don't have to go down a bad route or a bad route whenever you're trying to solve it. So I would heavily suggest graphing them before you try to approach the problem. All right, that's 35.5. I know this is just a beast of a section. It's a huge section. So try your best, and I'm sure we'll be talking more about the homework in class.